Alright, I'm in a bed. Science. Okay, so basically what we're doing is nuclear reactions, which is kind of like, what's it radiating? Alpha particles, beta particles, gamma rays. That's what we're doing. I'm on number 15 out of 18. The question is this. The isotope samarium-146 is produced when an element undergoes an alpha decay. So what we're going to want to do is we're going to want to find the element, right? So I've already set up the equation here. The blank element, right? This blank element, it goes under alpha decay. That's a 4, that's a 2, and that's an A for alpha. Right? So when it goes under the alpha decay, it leaves behind one alpha particle and one samarium 146, and down there is a 62. So it's 146, 62, samarium. Right? Because atomic number is 62. 146 is the isotope. So what we're going to want to do, in order to, no, it doesn't work. In order for us to figure this out, we are going to do the top numbers. So 146 plus 4. So grab our calculators here. 146 plus 4 is going to get us 150. So I'm going to go over to my blank and I'm going to write 150 right up there in the top. See that on the blank? I wrote 150 up there, right up there. Then we're going to do 62 plus 2. That's going to get us 64. Now we must realize, what are the numbers I'm adding? I'm simply adding these two top numbers to get this top number, and these two bottom numbers to get this bottom number. That's all I have to do. And see, that bottom number is the atomic number. Now, that's how we find the element. We just look for the element that has that atomic number, and that's the one. So how are we gonna find the elements on a calculator? I don't have a periodic table in here. I need to use my calculator. We're gonna go, and we're gonna click the apps button. It's gonna bring up a bunch of apps, right? The 8th app says periodic. I know you can't really see it on here too well. See right there, periodic. So you can just click the number 8. And it's going to bring us there. It's going to look like that. It's going to say click any button. There's our periodic table. We're just going to shift through it until we find element number 64. Which is gadolinium. GD. So in the blank, we're just going to write GD. Okay, so now, if I were to look at our equation, it'd be GD 150, right? When it decays, it's going to leave behind one particle, and it's going to decay into samarium 146. So basically, once the gadolinium is done, you're going to be left with an alpha particle and samarium 146. So that's how they do like carbon dating and stuff. Seeing the decay. How much has it decayed? How many particles have broken from the nucleus? Alpha particles and gamma particles are particles that have broken from the nucleus because radiation is when the nucleus has too much energy, and the particles, right? Particles in the nucleus don't just do this. They are like trying to get away from each other, right? Because neutrons are what? Neutrons are the same charge. So they're trying to get away. Strong nuclear force brings them back together. So they're going like this. When they have too much energy, sometimes some of the particles break away, right, from the strong nuclear force, and they fly out of the atom. That's radiation, right? Sometimes they break away. You know why they break away? Because it's an imbalance. So a neutron, sometimes when there's too many in a proton-rich environment, this neutron will convert into a proton, now even more protons, so that neutron is going to blast out of there with so much energy, right? That is an alpha particle. When a proton converts, is it this? I don't know. Then there's another one where another one converts to a beta particle and it blasts out of there at high energy, high speeds, and that's also radiation. But beta, and then sometimes you get antimatter when the proton converts into this, and then it leaves behind a positron, which is the opposite of an electron because it's positive charge, and antimatter, and they collide, those two pieces of matter break apart. But anyway, and they turn into pure energy. But yeah, I'm getting beside myself. We got to get on to question 16 because I have 18 questions. So, question number 16 is the beta decay of dysprosium 165 creates a new element. So it's asking us to find what is that new element. So I'm going to write out dysprosium 165. I've never heard of dysprosium before. Okay, so it's dy, that's a symbol. So we're going to write 165 on top, then 66 below, and then dy, showing that it's dysprosium 165 and the atomic number is 66, and an arrow because this is the stuff that goes into it, and we're going to try to find the results. It's doing beta decay. The symbol for beta decay looks like a negative and then an IE, but no, it's a small little 0 on top of a -1 and then an E. It looks like an IE, but no, it's a -1, 0, E. Okay, so it's going to leave behind that beta particle, and we have to find what is the element that it will turn into. Now, how do we do this? You might be asking, how in the world do I do this right now? Like, this is backward. How am I going to find this new element? Well, we just subtract the numbers on top and subtract the numbers on the bottom. So, what's 165 minus 0? 0. So the number on top again is going to be 165 for a new element. What's 66? Minus -1. 67. I'm not joking. Okay? Now, which element has the atomic number 67? Let's find out. Holmium, HO. So, the element that is produced is holmium. Holmium 165. The isotope of holmium 165, which has the atomic number of 67. Let's break down the equation, right? The something dysprosium or whatever that is. It's not loading my homework right now. Okay. Anyway, let's say the dy, right? dy, isotope 165, wrote the 165 there. Atomic number 66, right? So it's dy 165, beta decay, right? And it turns into holmium 165, atomic number 67. That's alpha, beta decay. The equation has gamma in it. Gamma has no mass, so you're subtracting 0 or you're adding 0, so it has nothing to the equation. So all these equations have gamma, right, in it. I just don't need to include it because it doesn't do anything to the equation.